Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine an explosion so violent, just so incomprehensibly massive, that it outshines all the stars in the observable universe combined.
Right, every single one.
Yeah. I want you to picture an event that releases more energy in a fraction of a second than our own sun will produce in its entire, 10 billion year lifespan.
Exactly.
And yet, if you were, say, floating in space right next to it, you wouldn't see a blinding flash. You wouldn't hear a deafening roar.
Nothing. It happens in complete pitch black silence.
Which is just wild to wrap your head around. The only way you would even know it occurred is that the literal fabric of space and time around you would stretch and squeeze.
Right. You wouldn't just feel it. The actual geometry of your own body would momentarily distort.
Okay, let's unpack this. Because yesterday, July 1st, 2026, our understanding of the universe fundamentally changed.
You really did.
We're looking at the release of the Gravitational Wave Transient Catalogue 5.0, or GWTC5. And the sheer scale of what we were talking about here is almost difficult to process.
It's staggering.
We are talking about 161 newly identified black hole collisions. And this was detected in just a 10-month window, right? Between April 2024 and January 2025.
Yeah, and it is a monumental threshold for astrophysics. To put that in perspective, those 161 new events bring our total number of known confirmed black hole collisions to a staggering 390.
Wow. 390.
Right. We are no longer in the era of viewing black hole mergers as these incredibly rare, one-off anomalies that we might catch if we're extremely lucky.
Right. We're not just hoping to get lucky anymore. We're practically taking a census.
Exactly. We are uncovering an entire hidden population because for the longest time, astrophysics was fundamentally constrained by the electromagnetic spectrum.
Meaning light.
Yeah, light. If you think about it, everything we knew about the cosmos came from catching light. Radio waves, X-rays, visible light.
Yeah.
But black holes, by definition, trap light. They are the ultimate cosmic ghosts.
Because the gravity is so strong, nothing escapes.
Right. So we only knew they existed because of how their gravity bullied the matter around them. Stars whipping around an invisible center, or accretion disks of superheated gas glowing as they fell in.
Like seeing the wind blowing through trees rather than seeing the wind itself.
That's a great way to put it. But when two black holes collide in a dark, empty void, there is no light to catch. Total silence until we learn how to listen to gravity itself.
And the reason you need to know about this today is that we are crossing from a period of discovery into a period of archaeology.
Oh, absolutely.
It is like we just mapped the ruins of a lost cosmic civilization, and now we actually have enough data to understand how they lived, how they grew, and how they died.
Which is the most exciting part.
But before we get into the record-breaking, just mind-bending specifics of GWTC5, we have to talk about the how. A decade ago, in 2015, the very first detection of gravitational waves happened.
Right, the one that proved Einstein right a century after he proposed general relativity.
Exactly. But going from one detection a decade ago to, 3 or 4 a week today, how are we doing that?
So the engine driving this revolution is the International LVK collaboration.
Okay.
That is LIGO in the United States, which operates 2 massive detectors in Washington State and Louisiana. Then there's Virgo in Italy and K-ARA in Japan.
And these are those massive L-shaped vacuum tubes, right?
Yeah, kilometers long, where we fire lasers back and forth to measure the stretching of space-time. But to understand why we are suddenly catching multiple events a week, you really have to look at the unsung heroes of the hardware.
Who are they?
Specifically, the researchers at the University of Glasgow. They have been working on gravitational wave science since the 1970s.
Wait, the 70s? Long before we had any proof these waves could actually be detected.
Exactly. Long before...
Imagine dedicating 40 years of your career to building parts for a machine to detect something that might not even be measurable.
It takes a lot of faith in the math.
I want to drill down into what they actually built, because I know it's not just a matter of pointing a telescope at the sky.
Yeah.
They had to solve an absolute mechanical engineering nightmare.
Oh, a total nightmare. What's fascinating here is that the core of the problem is isolation. The Earth is a remarkably noisy planet.
Right.
You have trucks driving on highways miles away. You have ocean waves crashing against the continental shelf. You have continuous microseismic tremors.
Constant vibration.
Always. Even the wind pushing against the observatory buildings creates ground tilt. If you just bolted a highly sensitive mirror to the floor, it would shake violently.
And we were trying to measure a change in distance caused by a gravitational wave that is smaller than a fraction of an atomic nucleus.
Right. So the background noise of the Earth is orders of magnitude louder than the signal we want.
It's like trying to hear a single pin drop in the middle of a roaring hurricane using a microphone you've suspended by a thread.
That is exactly what it's like.
So how do you separate the mirror from the planet it's sitting on?
You suspend it, but you can't just hang it with steel wire.
Why not?
Because steel has internal friction. When atoms in a metal wire rub against each other, they generate thermal noise, microscopic vibrations that would travel right down to the mirror and mimic a gravitational wave.
Oh, okay.
So the Glasgow team's solution was to develop ultra-sensitive mirror suspensions using fused silica, essentially extremely pure glass.
Wait. They are hanging 40-kilogram optical mirrors with glass thread.
Yes. They literally pull these fused silica threads so they are incredibly thin, and then they physically weld them to the sides of the mirrors.
Wow.
It's called a monolithic suspension. Because it's glass to glass, there are no joints, no clamps, and virtually no mechanical friction.
Which means no thermal noise.
Exactly. When you eliminate that friction, you eliminate a massive source of the noise. The mirror essentially floats, completely decoupled from the chaotic molecular vibrations of the Earth.
That's incredibly.
It sits perfectly still, waiting for the fabric of the universe itself to ripple through it.
I just want to pause on that image for a second.
Yeah.
We have a 40-kilogram mirror hanging by glass threads, isolated so perfectly that it doesn't feel a truck driving by outside. But it does feel two black holes crashing into each other a billion light years away.
It's beautiful engineering.
Yeah.
And it goes even deeper than mechanical isolation. We also have to fight quantum noise.
Right, because when you get down to measurements smaller than a proton, the universe just stops playing by normal rules. The Heisenberg uncertainty principle kicks in.
Exactly. At that scale, you can't know both the phase and the amplitude of the laser light with perfect precision.
Right.
Empty space itself is boiling with quantum vacuum fluctuations, virtual particles popping in and out of existence, randomly kicking the mirrors.
Which is just wild.
It is. So the observatories use a technique called quantum squeezing. They literally manipulate the quantum state of the laser light. They choose to accept more uncertainty in a variable they don't care about, like the phase, so they can squeeze down the uncertainty in the amplitude.
Because the amplitude is what they actually need to measure the wave.
Precisely.
It's like squeezing a balloon. You squeeze it in the middle to make it narrower where you need it to be, but it bulges out at the ends. We are physically pushing the quantum fuzziness out of the way of our measurement.
That's a perfect analogy. And it's this relentless, obsessive upgrading that gives us catalogs like GWTC5. What's fascinating here is the way the validation cycle works.
Oh, so?
The LVK collaboration operates in cycles. They don't just run the machines forever. They have observing runs, and then they completely shut down for months of commissioning.
Right, to install the upgrades.
Exactly. They install better lasers, heavier mirrors, better quantum squizzers, and more advanced glass extensions. And every time they turn the network back on, the sensitivity volume, meaning the total amount of space we can listen to, increases by a massive cube factor.
Okay, but here's the question that always trips me up. We have this hypersensitive glass pendulum, and it wiggles. How do the scientists actually, sitting at the computers, know for sure that the wiggle was a black hole in another galaxy and not just a weird microscopic thermal burp in the glass or a rogue quantum fluctuation that slipped through the squeezing?
Well, that is the defining challenge of data analysis in this field. Finding a gravitational wave isn't just looking for a bump on a graph.
What are they looking for?
You are searching for a highly specific mathematical pattern called a chirp.
A chirp.
Yeah. As two black holes spiral closer and closer together, they orbit faster and faster. This causes the gravitational waves they emit to increase in both frequency, so the pitch goes up, and amplitude, so it gets louder.
Yeah, I can picture that.
It looks like a very distinct, sweeping curve in the data. And to quantify their confidence, researchers rely on a metric called the signal-to-noise ratio, or SNR.
So if the background noise of the instrument is the static on an old analog TV, the signal is the actual broadcast trying to punch through.
Exactly.
For anyone familiar with signal processing, what is the usual baseline for claiming a real detection?
For a typical gravitational wave detection, an SNR of around 8 or 10 is usually the threshold where the team feels confident that they have a real astrophysical event.
Okay, 8 or 10 means it's real, not just a random statistical fluctuation of the noise floor.
Right.
Which sets the stage perfectly for the absolute bombshell of the GWTC5 catalog.
All right.
Because we are moving from the general how of detection to a specific event that I can only describe as the loudest whisper in the cosmos.
Oh.
Let's talk about January 14, 2025.
Event GW250112. This is an event that will be heavily cited in physics textbooks for decades.
Really?
Oh, absolutely. The black holes involved were massive, roughly 32 and 34 times the mass of our sun. They collided over 1 billion light years away. But the defining characteristic wasn't just the mass, it was the clarity.
Okay, you just said an SNR of 8 is a solid detection. What did GW250114 come in at?
It achieved a record-breaking signal-to-noise ratio of 76.9.
76.9. I mean, mathematically, that isn't just peaking above the noise floor. That is standing on a mountain with a megaphone. If an SNR of 8 is a blurry, grainy Polaroid of a black hole, an SNR of 76.9 is like a 4K, ultra-high-definition, uncompressed video.
That's exactly what it is. It is the clearest gravitational wave signal humanity has ever recorded. And when you have a signal that pristine, the entire nature of the science shifts.
How so?
You transition from merely cataloging the demographics of black holes to fundamentally stress testing the laws of physics. Dr. John Veitch, a researcher analyzing these signals at the University of Glasgow, noted that this unprecedented loudness allowed them to perform the most precise test of general relativity to date.
Wait, what are we actually testing, though? We know general relativity works. I mean, GPS satellites use it. Previous gravitational waves confirmed it.
True.
What does a 76.9 SNR let us look at that we couldn't see before?
It lets us look at the deeply warped space-time immediately before the merger and compare it with exquisite precision to the warped space-time after the black holes become one single object.
What?
And by doing that, they provided stunning confirmation of Stephen Hawking's black hole area theorem.
Oh, this is where the physics gets incredibly trippy. Let's break down the area theorem because it completely defies human intuition.
It really does.
When we talk about the area of a black hole, we are talking about the event horizon.
Right.
The point of no return.
Right. And it is crucial to remember that the event horizon is not a solid physical surface.
Right. It's not like the crust of the Earth.
Or the surface of an ocean, exactly. It is a mathematical boundary in space where the escape velocity exceeds the speed of light. Decades ago, Hawking theorized that in any physical process involving black holes, the total area of their event horizons can never decrease.
Never decrease.
Right. If two black holes merge, the area of the new single event horizon must be strictly greater than the sum of the areas of the two original black holes.
See, I know this sounds straightforward, but think about a water droplet analogy. If you take two separate water droplets on a windshield, and they merge into one larger droplet, the total volume of water is conserved. But the total surface area of that new single droplet is actually less than the surface area of the two separate droplets combined.
Because that is how three-dimensional geometry usually works.
Exactly. But for a black hole, the rules are inverted. The surface area must go up. And again, this isn't physical matter expanding. It's a boundary of gravity.
Right.
And GW250114 proved observationally that this invisible boundary physically grew exactly as Hawking's math demanded.
It is a profound confirmation, but the implications go much deeper than geometry. Hawking's proposal wasn't just a quirk of relativity, it was the bridge to thermodynamics.
Oh.
Hawking, alongside Jacob Bekenstein, realized that the area of a black hole's event horizon is mathematically analogous to entropy.
Okay, assuming everyone listening knows the second law of thermodynamics. Entropy, the measure of disorder, always increases in a closed system. It's the arrow of time. It's why you can't unscramble an egg and why a hot cup of coffee inevitably cools down. But applying the rules of a scrambled egg to a tear in space-time, that just feels wrong.
It sounds absurd until you look at the math. The Bekenstein-Hawking formula explicitly links the entropy of a black hole to the surface area of its event horizon. The area is the entropy.
Oh.
So when these two massive black holes in GW250114 merged, it wasn't a clean, silent fusion. The newly formed black hole was violently distorted. It literally rings like a bell, radiating away an enormous amount of energy in the form of gravitational waves as it settles down into a perfect sphere.
Okay, wait. If it is radiating away massive amounts of energy, shouldn't it be losing mass?
Yes.
And therefore shrinking? And if it shrinks, wouldn't the area and the entropy decrease, which violates the second law of thermodynamics?
That is the exact paradox physicists wrestled with.
Oh, really?
Yes. But analyzing the exceptionally clear waves from that ringing phase, the ring down, confirmed that despite throwing off several suns worth of energy during the merger, the geometry of a black hole is such that the total area still increases.
That is wild.
The mass lost to gravitational waves is more than offset by the way the remaining mass configures itself.
Okay.
This raises an important question, though, and proves definitively that the laws of thermodynamics, the exact same equations that govern steam engines, heat flow, and the arrow of time on Earth, apply to invisible gravitational boundaries a billion light years away.
Here's where it gets really interesting, though. The mechanics of a 19th century steam engine governing the event horizon of a black hole. It's poetic.
It is.
But if we are applying thermodynamics, I have to ask about temperature, because I know there's a severe counterintuitive quirk here regarding how black holes handle heat.
You're referring to negative heat capacity.
Yes. If you're listening to this and wondering how on Earth a massive black hole can be cold, you aren't alone. Because on Earth, if I pump energy into a system, like if I throw a log on a campfire, the fire gets hotter.
Natural.
But a black hole does the exact opposite.
It completely upends our standard thermodynamic intuition.
Yeah.
For a normal object, temperature is a measure of the average kinetic energy of its particles.
Right.
But black holes emit thermal radiation, Hawking radiation, due to quantum effects near the event horizon. And the mathematics dictate that the temperature of this radiation is inversely proportional to the black hole's mass.
So as the black hole eats matter, gets heavier, and its event horizon grows, its temperature actually drops.
Drastically. A black hole with the mass of our sun has a temperature of about 1/10,000,000th of a degree above absolute zero.
That is incredibly cold.
It is. But the newly birthed black hole from GW 250114, which was over 60 times the mass of our sun, it is exponentially colder. Supermassive black holes at the center of galaxies are some of the coldest objects in the known universe. As they gain energy and mass, they cool down.
I just love picturing this. You have this newly birthed Leviathan, born from an explosion of gravitational energy, ringing in the absolute freezing dark of space. And it is fundamentally colder than the empty space around it.
It's a haunting image.
And we only get to verify these incredibly exotic, almost philosophical truths because a glass thread in Washington State didn't shake.
It is the ultimate triumph of fundamental physics. But, physics is only half the story of GWTC5.
Right. A loud signal is a godsend for testing Einstein and Hawking. But if we want to understand the actual architecture of the cosmos, we need to know exactly where these signals are coming from.
Exactly.
A sound in the dark is fascinating, but to map the room, you need to find the source. Let's look at the next major milestone in the catalog. Event GW240615.
Detected on June 15th, 2024. The black holes here were roughly 26 and 30 times the mass of the sun. But the standout metric is the distance and the localization.
How far away was it?
This collision happened more than 3 billion light years away.
3 billion. Which means the ripples we felt in 2024 started their journey when life on Earth was barely figuring out multicellularity.
Exactly. But despite traveling for 3 billion years, this event holds the record for the most accurate sky localization ever achieved for a gravitational wave source.
Wow.
The researchers managed to narrow its origin down to an area covering only 6 square degrees on the sky.
Now, anyone who follows astronomy knows that a full moon covers about half a degree of the sky. So 6 square degrees is still a patch of sky holding 12 full moons.
Right.
To an optical astronomer with a telescope, that's a massive, blurry area. But in gravitational wave astronomy,
it is practically a pinpoint. Historically, gravitational wave localizations could span hundreds, sometimes thousands of square degrees, an entire hemisphere of the sky.
basically just saying it came from up there.
Right. So narrowing it down to 6 square degrees is a revolutionary leap in precision.
How did we suddenly get that precise? Was it a hardware upgrade to the LIGO lasers, or is this a software trick?
It was primarily about geometry and the vital return of the Virgo detector in Italy.
Okay.
Virgo had been offline for upgrades during the previous run, but its return allowed the LVK collaboration to use all three major detectors simultaneously. The two LIGO facilities in the US plus Virgo in Europe form a massive intercontinental triangle.
So it's essentially a cosmic GPS system.
Yes.
If you only have one cell tower pinging a phone, all you know is the phone is somewhere within a huge radius.
Yeah.
2 towers give you intersecting points, but 3 towers let you drop a pin on the exact street corner.
Exactly. Because gravitational waves travel at exactly the speed of light, they wash over the Earth and hit the different detectors at slightly different times.
Like fractions of a second.
We are talking about milliseconds of difference. The time it takes light to travel through the crust of the Earth from Louisiana to Italy. By precisely measuring those tiny time delays, scientists can calculate exactly where in the sky the wave originated.
Think about that. We are using collisions that happened 3 billion years ago as cosmic yardsticks to measure how fast the fabric of space is stretching today. Okay, I understand the triangulation, but why is the astronomy community so obsessed with the exact zip code of a black hole?
What do you mean?
Well, what is the broader scientific value of knowing which specific galaxy this happened in?
Because it is the key to solving the biggest crisis in modern cosmology, the Hubble tension.
The expansion rate of the universe.
Yes.
Yeah.
The universe is expanding, and the rate at which space is stretching is defined by the Hubble constant. But we have a severe problem.
It's the problem.
When we measure the expansion rate by looking at the early universe, meaning the leftover radiation from the Big Bang, the cosmic microwave background, we get a value of about 67 kilometers per second per megaparsec.
Okay, 67. But when we measure it locally, in our present-day universe, using standard candles like Cepheid variable stars and supernovas, we get a faster rate, right?
Right.
Around 73 kilometers per second per megaparsec.
Yes. And both sets of measurements have been refined to the point where the error bars no longer overlap.
Oh, wow.
They are both highly precise, yet they disagree. It implies there is something fundamentally broken or missing in our standard model of cosmology.
Which is terrifying for physicists.
It is. So gravitational waves offer a completely independent third way to measure the expansion. They act as standard sirens.
Standard sirens. Because unlike light, gravity doesn't get blocked, scattered, or dimmed by interstellar dust.
Exactly. With light, determining true distance is notoriously difficult. A star might look dim because it's far away, or it might look dim because there's a cloud of dust in the way.
Right, there's ambiguity.
But with a gravitational wave, general relativity allows us to calculate the absolute luminosity distance directly from the amplitude and the frequency evolution of the wave itself. Yes. The math gives us the distance purely from the strain on the detector. No intermediate stepping stones required.
But to get the expansion rate, distance is only half the equation. We also need to know how fast that object is receding away from us due to the stretching of space.
Right. You need the redshift. And gravitational waves alone cannot give you the redshift. To get that, you have to find the specific host galaxy where the merger occurred and analyze the light from that galaxy.
Right.
If your gravitational wave localization is a huge, blurry smudge covering 10,000 galaxies, you have no idea which galaxy's light to measure.
So by pinning GW 240615 down to just 6 square degrees, it becomes dramatically easier for optical telescopes to sweep that small patch, identify the host galaxy, and get the redshift.
Precisely. And this new catalog didn't just rely on this one incredible event. Alex Papadopoulos, a researcher at the Institute for Gravitational Research, noted that GWTC5 utilized 236 signals for this Hubble constant analysis.
236. That is almost double the number of signals used in previous catalogs. And in statistics, sample size is everything.
It really is. Each individual black hole merger contributes a small probability distribution, a piece of the puzzle regarding the expansion rate. By mathematically combining 236 of them, the error bars shrink dramatically.
I can imagine.
But processing that volume of data isn't something you can just run on a standard desktop.
Which brings us to the software. Because you have 236 immensely complex, multi-dimensional waveforms, and you have to cross-reference them with massive optical galaxy catalogs.
Yeah.
What was the bottleneck before, and how did they fix it for this release?
The computational bottleneck lies in Bayesian inference. To map the parameters of a gravitational wave, mass, spin, distance, sky location, supercomputers run Markov chain Monte Carlo algorithms.
Okay.
They generate millions of simulated waveforms and compare them to the actual noisy data to find the best fit. Historically, this took weeks or even months of continuous supercomputer time for a single event.
Just to process one event.
Yes. But the Glasgow researchers developed and tested entirely new software architecture for this catalog. They optimized the likelihood evaluations so aggressively that the analysis runs more than 1,000 times faster.
1,000 times faster. That isn't just an upgrade. That is a paradigm shift in data science.
Yeah.
You go from waiting a month for an answer to getting it while you're at lunch.
And that speed isn't just about impatience. When you can run a highly complex statistical model in minutes, you can vigorously test the robustness of your results.
Right.
You can inject artificial errors, tweak the cosmological priors, and run thousands of different scenarios to ensure that the final number you publish for the Hubble constant is bulletproof.
It is computationally iterating on the architecture of the cosmos. So we've used the loudest signals to test thermodynamics. We've used the precisely located signals to map the expansion of space. But yesterday's catalog revealed something else, something about the actual identity of these black holes that completely rewrites stellar biology. You can call it that.
We are talking about the family trees of the cosmos, the discovery of hierarchical mergers.
For the longest time, the narrative was simple. A massive star runs out of nuclear fuel, the core collapses under its own immense gravity, and you get a black hole. It's the final endpoint of a star's life.
Right.
But events GW2411011 and GW2411110 are screaming that this isn't the whole story.
No, it's not. These two highly unusual mergers were detected a month apart in late 2024. One was about 700 million light years away, the other much further at 2.4 billion light years. And what flagged them immediately in the analysis wasn't their distance, but their intrinsic properties.
Which properties?
Their masses and their spins.
Let's dive deep into the spin mechanics.
Yeah.
Because when a star collapses, conservation of angular momentum dictates that the resulting black hole should spin, right? Like an ice skater pulling their arms in.
Yes. The Kerr parameter, which measures a black hole spin, it's crucial here. However, when we observe typical first-generation black holes, meaning those born directly from collapsing stars in a binary pair, their spins tend to be relatively low. Furthermore, because those two stars likely formed together from the same swirling cloud of gas, their rotational axes are usually aligned with their mutual orbit. They spin in the same direction they orbit.
But these two new events in GW-TC5 broke those rules completely.
Completely. They featured highly unequal masses, meaning one black hole was significantly bulkier than its partner.
Wow.
But the smoking gun was the spin. They exhibited distinct, high-magnitude spins that were drastically misaligned from their orbital axis.
If they didn't form together from a collapsing star system, how do you get a lopsided pairing with wild, misaligned spins?
You get it because you are looking at a second-generation black hole.
The second generation.
The larger black hole in these systems wasn't born from a star. It was born from a previous black hole merger.
It's a Frankenstein's monster.
It is the product of cosmic recycling. When two first-generation black holes merge, the resulting single black hole absorbs a massive amount of angular momentum from the orbital energy of the collision itself.
It gets spun up.
Exactly. It gets a spin kick. The resulting second-generation black hole spins incredibly fast, often reaching a Kerr parameter of 0.7 or 0.8, which is near the theoretical maximum.
That's insanely fast.
And crucially, the direction of that new spin is dictated entirely by the chaotic geometry of the collision, meaning it will be randomly oriented relative to any future partner it finds.
So, what does this all mean? I picture this like a heavyweight demolition derby. It's not just a peaceful binary star system quietly living out its days and collapsing. It is the winner of a previous collision finding another black hole, capturing it, and colliding again. We are looking at the heavyweight champions of the universe.
That's a great analogy.
But that requires a highly specific environment, doesn't it?
Yeah.
Space is overwhelmingly empty. If two black holes merge in the quiet spiral arms of our galaxy, the resulting second-generation black hole is just going to sit there alone in the dark forever.
It has no one else to interact with. To get hierarchical mergers, you need a dense, highly populated environment. You need a cosmic factory floor.
Where are these factory floors?
We believe these environments are globular clusters. Ancient, tightly packed spheres containing millions of stars orbiting the outskirts of galaxies.
And the dynamics inside these clusters are wild. Because black holes are heavier than the average star, over millions of years, they experience dynamical friction. They essentially sink to the very center of the cluster.
Mass segregation. You end up with a dark core, a swarm of black holes furiously buzzing around each other in a highly confined space. And in this chaotic swarm, three-body interactions become common.
Break down a three-body interaction for us.
Imagine two black holes orbiting each other. A third black hole flies close by. The gravitational interaction is incredibly chaotic.
Like a gravitational mosh pit.
Pretty much. What usually happens is the lightest of the three black holes gets gravitationally slingshotted out of the system at high speed. But to conserve energy, the remaining two black holes are forced into a much tighter, closer orbit.
Which dramatically accelerates their eventual collision.
Yes. They merge, creating a massive, highly spinning second-generation black hole. And because it is sitting in the middle of this dense swarm, it doesn't take long for it to gravitationally capture a new partner and start the process all over again.
This changes the entire paradigm of stellar evolution. And what blows my mind is that this isn't just a fringe theory based on two weird outliers anymore. The catalog proves this is happening at scale.
If we connect this to the bigger picture, Storm Columns, a postgraduate researcher, focused specifically on this. They analyzed 267 sources from the catalog, including over 100 brand new observations, to measure the masses, spins, and distances. This is where the field matures into deep demographics.
We aren't just finding a few interesting houses, we are running a census on the entire hidden city.
And the census data shows a clear correlation. Black holes in different mass ranges consistently exhibit different spin characteristics. The signatures of hierarchical mergers persist across the population. It proves definitively that the universe has multiple formation pathways. It is actively running assembly lines in these dense stellar clusters, forging increasingly massive black holes from the remnants of smaller ones.
It is breathtaking to step back and look at the trajectory we are on. In less than 10 years, we have gone from, hey, we finally built a glass pendulum quiet enough to prove these invisible ripples exist, to here is a highly optimized, Bayesian-mapped demographic breakdown of multi-generational black hole factories across billions of light years, complete with thermodynamic stress tests of their event horizon.
It's moving so fast, and the statistical power is only going to grow. As the observatories upgrade for their next runs, we will transition from hundreds of events to thousands.
Which brings a quote to mind from Dr. Daniel Williams, the co-chair of the LSE's Compact Binary Science Working Group. He said that looking at this massive catalog is the astronomical equivalent of uncovering an ancient civilization.
It really is.
We aren't just logging individual deaths of stars. We are revealing the underlying infrastructure of a lost world. We are seeing how these dark leviathans congregate, how they grow, and how their violent interactions shape the very galaxies they inhabit.
It is a profound realization. We are mapping the dark skeleton of the universe.
So the next time you step outside on a quiet night and look up at the dark sky, I want you to remember that it is not still. It is not silent. The empty space between the stars is actively ringing with the echoes of invisible giants colliding. We are sitting on the shore of a cosmic ocean, and finally, we can hear the waves crashing.
Beautifully said.
But before we wrap up, I want to leave you with one final thought, something to chew on based on these dense globular clusters and second-generation black holes. We know these environments act as factory floors, forcing black holes to merge, creating heavier, faster spinning offspring.
A cosmic billiard table.
Right. But if that environment is so crowded and the three-body interactions keep tightening orbits, could this process theoretically continue without end? No. If a second-generation black hole eats another black hole, it becomes a third generation and then a fourth. Is there a physical limit to how massive a black hole can grow purely through this bumper car style of cosmic evolution before they alter the very galaxies they live in?
That is the bleeding edge of the science right now.
Yeah.
The limiting factor is the gravitational recoil.
Recoil.
When two black holes merge, the resulting gravitational waves aren't emitted perfectly symmetrically. This gives the new black hole a massive kick, sending it hurtling through space.
Like a rocket effect made of pure gravity.
Yes, and sometimes that kick is so violent that the recoil velocity exceeds the escape velocity of the globular cluster. The new black hole is literally shot out of the cluster into the empty intergalactic void, terminating its growth forever.
But what if it's already so massive that the kick isn't enough to eject it? What if it survives the recoil, sinks back to the center of the dark core, and eats again? We could be on the verge of discovering third, fourth, or fifth generation black holes. We could literally be watching the mechanical process that eventually builds the supermassive black holes sitting at the centers of galaxies. And we will only know because we figured out how to measure a shift smaller than a fraction of an atomic nucleus. The universe is incredibly loud, my friends. You just have to know how to listen.